Welcome back to retrofitting a classic Volkswagen Beetle to electric. This video will be a bit more technical, giving an overview of the design. In the previous video I said that we visited electric classic cars from which we ordered our conversion kit, and they showed us how to install this kit. But just as a side note, this video is meant to reflect how they did it, so there might still be some minor changes to these designs that reflect our requirements. So, kit specifications. The kit consists of a Hyper 9 motor and Hyperdrive X1 controller with a peak power of 95 kilowatts, and they are kind of made to work together, so there is very little development from our side necessary to make them work. Then 5 Tesla Model S battery modules for a total pack capacity of 32 kilowatt hours, and we estimate the range will be about 150 kilometers. Each battery module has a voltage of about 25 volts, so we will connect these obviously in series to get a high voltage system of about 125 volts peak. The low voltage system will consist of a 12 volt lead acid battery, and that will be grounded to the chassis of the original vehicle. The high voltage system will be completely isolated. The low voltage system will be used to power the original electronics such as the lights and the horn and so on. We have an Alcon 500 watt DC to DC converter to charge this low voltage system. Then a Thunderstruck Motors dilithium design BMS master control unit. So this unit speaks to the next line, which is the 2 Thunderstruck Motors BMS satellites, which is connected directly to the battery cells, and so these satellites monitor the cell voltages and communicate this data to the BMS master control unit, which can take certain actions such as shut down the system if the voltages get too low. Then the Thunderstruck Motors ground fault monitor that constantly monitors the isolation between the high voltage and the low voltage system, and if that goes below a certain threshold, this can cut also the high voltage system off. An Alcon 6.6 kilowatt charger. This one can output 50 to 155 volts DC. It has CAN communications with which it communicates with the BMS master control unit to sort out the charging speed and so on. And finally we have a 3 kilowatt high voltage heater. So the Beetle has quite a unique vehicle layout, something you won't see from any other vehicle today. The differential and the gearbox is actually a single unit at the rear of the vehicle, and the engine used to sit even further back, connected to this differential slash gearbox. And then it has a swing axle, not independent suspension, swing axles that are directly connected on this differential gearbox unit. The logical question to ask then is, where do we put the electric motor there? Well, because we don't want to mess with any axles, we leave the gearbox differential unit in place and put the motor directly connected to this gearbox, exactly where the engine was. But this has the following implications. So the clutch is kept, and this means you can also shift on the fly while driving. We've been told that full power launches in first gear will shred the original gearbox gears, but that gears 2 to 4 have no issues really. Another thing to think about is that full power and 8,000 revolutions per minute will now be available even when you shift into reverse. So this means that we will probably have to implement some sort of reverse sensor telling the motor controller to go into a different profile that will limit the power or speed or something like that. Then the motor speed sensor will no longer be enough to log the vehicle speed, as it can be in any gear and you have no way of knowing that just looking at the speed sensor. Component placements. I should emphasize that these are the locations that electric classic cars used, and we will likely make a few changes here. So where the engine was, they put the charger, heater, and of course the motor and the motor controller. Between the back seat and the rear firewall is the rear battery box with 3 Tesla modules. Then underneath the back seat is the DC to DC converter, relays, the BMS master control unit, display, the 12-volt battery, and the throttle position sensor. Then under the front bonnet, they put the front battery box with 2 Tesla battery modules, and of course the charging plug where the fuel filler cap was. The high voltage connections. So let's start at the motor controller. 3 high voltage cables go directly to the motor itself, and then the motor controller gets its high voltage negative and positive from the front battery and the rear battery respectively, and then obviously a high amperage high voltage cable between the front battery and the rear battery, just so these batteries can be connected in series. Then there is an additional full pack negative running from the front battery to the rear battery, so that we have full pack negative and positive within the rear battery, and then we can plug all the ancillaries to the rear battery, such as the heater, the charger, and the DC to DC converter. And finally there is just the connection between the charger and the charging plug, which just connects the AC power to the charger. Now we're getting to the electronic bits. So the CAN connections are pretty simple, just a connection between the charger and the battery management system master control unit, and then also to the display, but the most important one is between the charger and the BMS MCU, which just communicates the charging rate and so on. Then also for the charging connections is the proximity pilot and control pilot connections from the charging plug to the MCU that allows the MCU to communicate with the charger it is being plugged into. So the BMS master control unit makes use of isolated SPI connections to communicate with the satellites, and this only requires 2 wires to communicate. So that's the 4 wires you see there. Then programming this BMS master control unit is pretty simple. You can program it with PuTTY over separate serial connection, and you just use specific commands. And with this you can set the charger and the fault parameters and so on. For the motor controls, it's pretty interesting to note that the battery management system has absolutely no knowledge of the throttle input or the brake input. This all goes to the motor controller, which uses this together with the motor's speed encoder and the motor thermistor to control the motor effectively. As I said earlier, the motor and the motor controller was designed for each other, so it's pretty easy to program them, and you use a GUI based software with a separate serial connection, and then you can set up all the parameters as you like. The only cooling components in the kit is for the motor controller and consists of a cooling plate, radiator, and coolant reservoir and pump. And the cooling requirements for the motor controller is not that demanding, so we're actually using PC components for these parts. Well, what else is there to think about? The BMS master control unit has hard and soft fault conditions, which are designed to take appropriate actions. The soft fault condition gives a signal to the motor controller to set the motor torque to 0, while the hard fault condition simply disconnects a main contactor, disconnecting the entire high voltage system. Triggers for a soft fault are when the voltage of a single cell is too high or too low, or when the charger is still plugged in, while a hard fault triggers when there is a hardware fault, dangerously high battery temperature, or the voltage of the entire pack is too high or too low, or if there is a cell temperature sensor or ground fault monitor that is missing. Furthermore, the inertia switch should disconnect the high voltage system in case of an accident. We have to put the main disconnect fuse somewhere. The high voltage fuses for the charger, heater and DC to DC converter need to be connected. We have to integrate with the existing wiring loom of the vehicle, as well as the ignition switch, which needs to power on the electric vehicle in an appropriate manner. We have to think about what happens when the high voltage battery goes low or when the low voltage battery goes low, and can someone easily remedy such a situation. We are going to use a display instead of analog gauges, and this also means microcontroller with CAN integration needs to be implemented. We are also going to be using a display instead of analog gauges. Electric classic cars use the stock analog gauges of the Beetle, which actually integrates nicely with the BMS MCU outputs. But we want to be able to see and log the motor speed, torque, power, and so on, so we'll likely use a display. The motor information is only available via CAN though, from the motor controller, and this means that we need to think about CAN integration, the various CAN protocols of the devices on the bus, and then we have to add a microcontroller that interprets these CAN messages and displays the correct information on the display. Then we have a buzzer that needs to go off when there's an open door. And then a big one, battery cooling. To give you a very brief overview, you can look at the graph on your right, which indicates the temperature of a single Tesla battery module at 117 amps, which equates to 45 watts of heat if you take into account the internal resistance of one of these modules. And this results in a temperature delta of about 10 degrees Celsius. Also keep in mind that lithium batteries are generally happy below 45 degrees Celsius. So you can imagine if this is what happens at 45 watts of heat, when you're going up a steep mountain pass, drawing 350 amps continuously, this will produce 400 watts of heat. And if it's a summer day in South Africa and can get up to 40 degrees Celsius, you can just imagine the temperature of the battery will not be below 45 degrees Celsius, and that is why we need to implement proper battery cooling. That's it from my side. Thank you for watching.